I feel the people are arriving. It seems to have leveled out. So if you want to make a start, that would be fantastic.
Great. Thanks very much, Christopher, and welcome everyone to this SuperGen Super Solar webinar on solar grid connectivity. To set the scene, with targets of 70 gigawatts of installed capacity by 2035, the required rapid growth in the deployment of solar voltaics presents challenges and opportunities for system developers, network operators, financiers, and consumers that the research community can address. This webinar hopes to address many of these challenges, and we have a lot of excellent speakers lined up for you. You can see all of them in front of you now, but before we move on to them, a little bit about the Super Solar SuperGen community. The SuperGen Super Solar community is an inclusive solar community linking together university researchers and industry, which started way back in 2012. It provides regular opportunities to early career researchers to share their work. I myself was lucky enough to benefit from some of these opportunities in my early career. And it also offers topics focused on different webinars, in-person events, and sponsored events. One of these is this webinar. Thank you all for joining, and we hope it's going to be a great discussion. You're very welcome to add questions to the comments. Please use the Q&A function on Zoom. Rather than the chat function, please use the Q&A. Please add questions as they come up for each speaker. There'll be time to address each of your questions after each talk. A bit more about SuperGen Super Solar. First of all, it's free to join and open to all. It currently stands around 750 members spanning across the disciplines of solar, so from students, academics, across industry, and many others too. We have regular email newsletters, which can give you updates about super solar projects and other PV events that you might be interested in. There's lots of funding opportunities, including international and industrial secondment projects. There's many super solar events that you're welcome to join. Of course, this is one, and also the in-person events too, and also support to attend different international conferences to share your work and learn from the work of others. There's also plenty of free places sponsored at UK events for super solar members, so all the more reason to join. Now, as we move on to why we're all here today, firstly, to introduce myself, my name is Dr. Philip Sandwell. I'm from the United Nations Institute for Training and Research. Much of my academic career was focused on how to connect mini-grids with national grids, normally in developing countries, and solar was the main component of that. We're joined by some excellent speakers. First up, we have Nikki Pillinger from Road Knight Taylor, followed by Alistair Buckley from the University of Sheffield. We then have Pat Wheeler from the University of Nottingham, Rina Sayani from the University of Sheffield, and Mark Letcher from Exeter University. The webinar will last around about until 3:30. So there'll be around 20 minutes for each speaker to present their topics, and then roughly 5 minutes of Q&A. Once again, please use the Q&A function in order for the speakers to address your comments. Without further ado, moving on to our first presentation from Nikki Pillinger from Road Knight Taylor. Nikki sits on a number of DNO's connection steering groups, Regen's Grid Connections Working Group, and Review of Electricity Market Arrangements Working Group, and the Solar Energy UK Grid Steering Group. Her presentation is entitled Introduction to the Grid, an excellent place to start. So without further ado, I will stop sharing my screen, and Nikki, the floor is yours.
Brilliant. Thank you, Philip. I will share my screen. Hopefully this is as seamless as it was earlier. Well, so I'm from a company called Road Knight Taylor. So we are grid connection consultants. So just a sort of very short introduction to me. So I did a degree in energy policy at the University of Exeter, and then sort of fell into the field of sort of power systems engineering, and specifically in sort of solar, electric vehicle, and battery storage industry. So my day-to-day is project managing large utility scale grid connections, normally sort of 10 megawatts up to about 250 megawatts or so. It's a very interesting space at the moment. I will go into a little bit later, but yeah, very, very challenging, the UK grid at the moment. But what I'm going to do initially is just chat you through kind of a little bit on how the grid works, and what kind of infrastructure we see on the grid. So hopefully, cool. So I always try and start by kind of explaining National Grid. So National Grid is, it's a company. we often hear the national grid referred to. So the national grid is all of the electrical infrastructure that we have in GB. So from, you know, very large transmission lines down to the infrastructure that comes into our homes. And especially in the media, this is mixed up quite a lot. Sort of people kind of use national grid and the national grid quite interchangeably. So just to clarify, National Grid is its own company. It's actually two companies, and they own the transmission system in the UK. So they've got the electricity system operator who do sort of balancing services. And to put it quite sort of simply, it's like the ESO do the kind of software part of the grid and the transmission system, whereas the transmission operator actually owns the grid hardware. So this is a map of the transmission system. So I like to call this the motorways of the electricity grid. So there's a little nuance that in Scotland, we have 132,000 volts as transmission. In the rest of the country, it's 275,000 and 400,000 volts. So as I said, this is kind of the motorways of the electricity system, and it's what we call the transmission system, and is owned by National Grid. So we've also got the distribution network operators. When I was at university, I didn't think I even knew what a distribution network operator was, and now I talk to them every single day. It's kind of a legacy from when we had more sort of when we had the publicly owned electricity networks. So there's 14 different license areas owned by 6 different DNOs. Depending on where you live, you'll have a different DNO. So I'm with National Grid Electricity Distribution, which was confusingly used to be called Western Power. It's now called National Grid because National Grid bought them last year. So to kind of just add more confusion around that whole National Grid piece. So part of the network infrastructure that we have different voltages on the electrical network. So this is a map of around where I live. So we have on the distribution network, we've got 132 kV, 33 kV, 11 and low voltage. On this map, the black line is 132, green is 33, and the reds are 11s, just to give you a little bit of an indication of sort of the amount of different infrastructure that we have. Sort of 11 kV is very much to go off to sort of smaller rural areas, whereas the larger voltages are to connect small, like larger towns and villages. So just to go into a little bit of the infrastructure that we see on a grid, we've got underground cables. These are normally used in urban areas or where it's sort of impractical to have overhead lines. There's also been some activities up in Scotland recently to actually underground overhead lines for more aesthetic reasons. So going through national parks, they've undergrounded some of the overhead lines that we had up there. So this is what the transmission network looks like, or at least the overhead transmission network. I live in Glastonbury, so just down the road we've got the Glastonbury Festival site down in Pilton. If anyone has been to that site, then these are the big transmission lines that you have going over Glastonbury Festival site. So that's what they look like. Then you step down slightly. So this is down to the distribution network. If you're very nerdy like me, you can go around and look at the amount of insulators on overhead lines to try and figure out what voltage they are. So these have got less insulators than, sorry, the insulators are the, if you can see my mouse, they're these things here. And then you go down to 33 kV, which is much smaller. As I said, these sort of are the ones that connect smaller towns and villages. And then you've got 11 kV, which is quite diddy and connects sort of more rural areas around. You might see them going out towards farms. And then you've got low voltage. I'm sure you've all seen these before. So these are pole-mounted transformers, and this transforms the voltage down to more like what we see in our homes. So on the electrical grid network, we've got substations. So the predominant operation of these is to transform voltage from one sort of higher to lower voltage. It also provides a point of control on the network. So I won't go into this too much, but there's different types of substations. Sort of, you wouldn't get like a 400 to 11 kV substation or anything like that. Not on the grid that we have anyway. So you have different sort of voltage step down levels. So this is sort of what's in a substation. I think we're sharing these slides afterwards, so if you want to look into this a little bit more, then please do. And this is just a little bit of an illustration of the different sort of things that we find in a substation. So as I said, they're a point of control. So different parts of the substation can be turned off or they can be reconfigured in order to serve different parts of the network differently, especially in storm situations. This is super important that we have the ability to serve different customers from different parts of the network. So I have done quite a lot of large solar work. And normally when we build a solar park or a wind farm or anything like that, we connect it to a point of connection in the grid, whatever voltage that is or whatever kind of infrastructure that is. It's all normally fairly nuanced. And we have to get a cable from there to wherever we want to build. So this picture is a very big cable. So this is an offshore wind cable. And it's just sort of picking up that we need to be quite cognizant of the impacts of that cable route and the potential sort of issues that we can see along the way. It's very obvious when these large transmission lines are done because they kind of have a lot more powers than sort of standard developers if you were going to build a solar park, for example, or EV charging or anything. But yeah, when you're putting this new infrastructure in, you have quite a lot of potential barriers that you come across. You have to be very cognizant of the ecology that you're coming across on that cable route. Whether you need to go down a road and any sort of arrangements you need there. If you need to do a directional drill, we've done directional drilling under motorways or under train lines before. If there's any rivers or anything in the way. It's planning cable routes. And when you're putting new infrastructure in, you have to be very, very aware of what impact you're going to have. So just a little bit on grid costs. So when we build solar parks, we've got non-contestable grid costs and contestable grid costs, and also customer costs. These are effectively just things that are done by different people. So the DNO actually do the connection into their network because it's their infrastructure. They understand it very well. And then you have other companies that potentially do the sort of the cable route, which is contestable, and then you've got your own customer works on site. Just a little bit of in case you ever hear this, because there's quite a lot of jargon in this industry. So if you ever hear the word ICP, that's a company that actually carries out works for new electrical infrastructure. So if you ever get involved in this sort of thing, you will normally have to hire an ICP to actually put that new network infrastructure in. So to build substations, put cable routes in, etc. We've also got another little nuance, which is IDNOs. So again, just a little bit of jargon explaining for you. So these are actually smaller DNOs that operate within the larger DNO network infrastructure. So as I said, my day job is quite a lot of engagement with the DNOs. So before we actually even put an application into them, we do quite a lot of engagement with them. So they have quite a lot of online tools that you can use if you ever want to have a look at grid capacity in your local area, or you can talk to them in a connection surgery. Or you can get budget estimates, which are of varying usefulness. And then we tend to put in a full application. So we actually then get a grid offer and then go through that sort of 4 or 5 year process of actually doing a grid connection. So again, I'd always encourage anyone to get involved in this industry. There's a huge amount of jobs that you can do within it. Building solar parks is very frustrating, but also super fun in my experience. And there's a lot of people that can be involved. So you've got your developer. So, I used to work for British Solar Renewables or GridServe, or there's LightSource, there's Low Carbon. There's so many amazing solar and wind and renewables developers out there. And then you've got your landowner that you definitely need to keep happy, otherwise they won't let you build anything. Funders, suppliers, which are super important, especially at the moment. We've got very long lead times on items of kit, so that's something to be aware of. Then you've got your engineering, procurement and construction who actually build your solar park, your ICP or your IDNO. And then you've got your contractors, people that actually come and do the electrical work, connecting everything up, putting everything in, doing inverters and doing all those communications between them. Obviously, you've got the DNO and National Grids, technical advisors and everyone's favorite lawyers, also sort of planning consultants and any other sort of consultancy services that you have to have involved during the build of a solar park. At the moment, so we've got quite a few issues on the grid at the moment. This isn't an exhaustive list, but there's quite a lot going on. So it's a really good thing that we've connected loads and loads of renewable generation to the grid. However, it wasn't designed for that. So we've gone from a very sort of top-down energy system to more of a bottom-up system where we've got a lot of distributed generators putting energy into networks that weren't really designed to flow that way. Electrical network infrastructure also has a very finite amount of energy that can flow through it and you know, safety is absolutely paramount in this industry. You know, every day I remind myself that this is very high voltage electricity. This is very dangerous, and our absolute categoric priority is keeping people safe. So the DNOs have to model their networks and make sure that what they're connecting is actually safe. So they have to look at things like fault level, thermal restrictions, any sort of voltage issues that they might get from a connection. Also within substations, you've got transformers and they have tap changers, which can only change at a certain rate. And any sort of transformer reverse power flow. So this is the power that you can put through a transformer sort of the other way. As I said, it's designed very much from top down. We've also got national grid network issues, which I will go into a little bit more on the next slide. So once we've actually got a grid offer, we then have that sort of legal basis of an agreement to connect into the grid. What the DNO then does is sends off something called a statement of works or modification application or project progression. There's lots of different words for this. But it's essentially them talking to National Grid and saying, you know, we're going to put this on our network. What impact is it going to have on your network? At the moment, because we've got so many things contracted on the network, we actually have 500 gigawatts of contracted capacity. This isn't connected capacity. This is contracted capacity on the GB grid. So kind of put that into perspective, our peak demand is about 4550. So yeah, it's a bit of a problem that we've got all this sort of theoretical generation that wants to connect into the grid. It's also really good, you know, it's super positive that we have so many renewable generators. But equally very challenging that we have, this huge potential reinforcement need to go on a grid. So a lot of distribution projects are delayed at the moment because of the amount of theoretical reinforcement that we need to be doing on National Grid's network. If you want any more information on that, then National Grid ESO have got quite a lot of information out on it at the moment. We've got a couple of tactics to sort of alleviate this. So we've actually got active network management, which is more of a flexible solution. So instead of just assuming sort of worst case on the network, so peak generation and lowest demand, we actually put various controls onto generators and within the networks to allow people to sort of constrain off their generation and at times of peak generation, so they don't have that sort of overloading impact on the grid. This works to a certain extent. We can do this with some sort of National Grid assets. But as I said, at the moment, we've kind of gone past active network management because we have so much contracted capacity on the grid. So at the moment, there's lots of things in play. There's a National Grid at ESO have a 5-point plan. The Energy Networks Association have a 3-point plan. And they're all essentially trying to alleviate the issues with all of this contracted connection that we have on the grid and also allowing people to connect a lot earlier. I think the last thing I would say about this is that there is quite a resource constraint at the moment in these industries. You know, it's very difficult to get even the sort of limited amount of generation that we have in progress at the moment, contracted and connected onto the grid. So I would encourage anyone that wants to come work in this industry. As I said, it's really fun. It can be really frustrating, but it's also really, really fun. You get to do a lot of, you know, I think the reason I'm here is because I get to see things be built. You know, I get to do something tangible. I get to, you know, see a solar park being built. I get to see the benefit that that's done. And yeah, that's probably it from me. So if there are any questions, hopefully I've been kind of on time. I did not look at what time I actually had. Yeah, I think I've done about 15 minutes, so hopefully that is okay. And if anyone's got any questions, please let me know.
Great. Thank you very much, Nikki. That was a great insight into a great introduction to the grid. Thank you very much. As a reminder, I'd like to invite anyone to add their questions to the Q&A function, so we can get those answered by Nikki for you. In the meantime, I have a few questions. I think the first one for me is, as we look ahead to the next 10, 20 or 50 years, and we're hopefully expecting a lot more renewables to come onto the grid, what kind of challenges do you foresee the network experiencing, and can you kind of give some insight into how they might play out over the kind of longest timescales?
So I suppose it's twofold, really. It's resource, which we have very limited amount of people who can actually do this anymore. And it's also money and it's time. So over sort of historically, Ofgem hasn't really allowed preemptive investment in networks. So that means that we have a very limited grid infrastructure for what we actually want to connect to it. And that means that reinforcement timescales, we had one of the statement of works come back the other day and it said, your project can't connect until 2043, which is mental. However, the ENA are actually putting things in place to sort of prioritize projects that are more sort of shovel ready, like projects that have gone through planning or are progressing with design. However, they would actually be connecting on more of a potentially constrained basis, which then makes it very challenging to model and also very challenging financially. The government has finally, thanks to Merlin from Regen, I don't know if anyone's familiar with Regen, but as part of one of our grid working groups, we sent a letter to Grant Shapps and said, this is a massive issue. This isn't okay. All these renewable generators are getting connection dates 15, 20 years out into the future. Can you do something about it? And National Grid has actually listened, and they have put in place this plan in order to remodel the impact of batteries, in order to actually look at their construction planning assumptions and enable more renewable generation to connect a lot earlier. As I said, the financing is very uncertain. There's still not a huge amount of certainty in terms of what markets these renewables and especially battery storage can play in. So there's not a lot of, when we had the FITs and the ROCs, there was very long-term certainty in terms of what you would earn from building a solar park, but we don't have that anymore. And also it's a huge amount of time, building on onshore. This is why they've got quite a lot of offshore network that they're planning. So there's the holistic network design, which covers all of the offshore infrastructure build, but onshore is very difficult because people really don't like big new pylons going over their towns, which is fair enough, really.
Yeah, for sure. It seems like a lot of these challenges are quite protracted, but I guess it means a lot of job security for people like yourself as well. So we have I'll call it 2.5 questions from the chat. The first question is from Chris Groves. If you'd like to put in your institution as well in your questions, please feel free to. The first question is from Chris Groves. He asks, what challenges will increased heat pumps and EVs pose for integration of renewables onto the grid? And a kind of secondary question from Chris is also, what are the grid issues related to rooftop solar? Nikki, what do you think?
So that's more sort of on the LV networks. So we've got these challenges on all parts of the network. So part of the issues with integrating heat pumps and that sort of new infrastructure is one is the lack of communication and the lack of visibility that the DNOs actually have on their LV networks. We are just going to need a huge amount more copper in the ground essentially to enable this. So there's kind of a twofold approach, which is when you're building a new housing estate, instead of having an average home demand of about 1 kilowatt, it's now going to be more like 7 or 8 if you have an electric vehicle charger and a heat pump. So it's building new network infrastructure very differently, but also, you need a lot more of it. You need a lot more capacity for much smaller amount of homes. If you build 1,000 homes now, that would used to be 1 megawatt. That's now potentially 10. That's a huge amount more energy that we need actually going into these systems. So a lot more network infrastructure essentially, and a lot more communication. So the DNOs actually have sort of real-time information on what's going on those LV networks. Rooftop solar, again, it very much depends what sort of scale it is and whether it's a retrofit or whether it's a new build. However, the challenges are kind of the same. It's actually having more infrastructure needed in order to enable those things to connect. Because as I said, electrical networks have a very finite amount of energy that you can actually push through them safely.
Great, thanks very much. Yeah, it seems like all these new technologies coming online, lots of new challenges to deal with. We have 2 more questions, and I think we'll have time for both, just about. So the first that comes from Pascal Keinberg, who concedes this might be slightly off topic, but regarding the many stakeholders involved in project planning, how does this compare to residential installations?
I wouldn't know, I've never done one. Yeah, residential installations, you don't have many people, you don't need planning. So, you know, this is for a big solar park. You know, there are hundreds and hundreds of people involved in building a big solar park along the sort of lifetime of that process. Whereas with rooftop solar, you have your homeowner, you have your installer, and then you've got the DNO as well, I suppose. It depends how you notify them. If it's a G99 application, then you have to put a full application in, which is above 3.64 kilowatts. If it's under that, then you just have to notify the DNO. So yeah, you really don't need that much. I don't know about planning. I think you might need planning in sort of conservation areas or something like that. But yeah, it's a lot less complicated.
Great, thanks. And if anyone does have any more experience with the residential side of things, please do put it in the chat. I think we have time for one last question from Mark Stadden, who says,
Hi, Mark.
Mark says, thanks, Nikki. Which areas of the UK/DNO regions are the most constrained? And are these areas being prioritized for investment, etc.?
Honestly, none of them are good. And they're sort of bad for varying reasons. I can catch up with you afterwards and let you know. But essentially, they all have constraints. They've all got transmission network constraints, whether it's because of wind, whether it's because of transmission applications, whether it's batteries. You know, some areas that aren't particularly suitable for solar have got batteries. In Scotland, there's a huge amount of wind, so the transmission network is very constrained because of that. Also just because of the huge amount of applications. So this is to hammer home, like, a lot of it is theoretical constraints because of the amount of applications that we've had to connect into the grid. Putting an application into the grid is not super difficult. So you can actually reserve capacity quite easily. But the grid has to assume that all of these connections are going to connect. Part of the National Grid 5-point plan is actually to reevaluate their construction planning assumptions to rejig what they assume is actually going to connect. So they're assuming about 33% is going to connect as opposed to 100, and they are remodeling their reinforcement need based on that. But yeah, it's everywhere. Basically, everywhere's rubbish.
Thanks,
and
Nikki.
all the DNOs have sort of got all their own nuances as well, because they've had different challenges historically. Like I said, in Scotland, they've had wind. In Cornwall, they've had solar and wind. UKPN, they've got solar. Northern Power Grid, it's batteries. Yeah.
Great.
Difficult everywhere.
Yeah, thanks for a very frank and honest summary, which is always appreciated. Like, there's no beating around the bush, so thank you very much. So we're out of time for Nikki. Nikki Pillinger from Road Knight Taylor, thank you very much for your presentation. Thank you.
Thank you.
Our next speaker is Alistair Buckley from the University of Sheffield. So Alistair leads the Sheffield Solar Research Group, who investigate solar photovoltaic power flows within the GB electricity networks, including national and regional, real-time and historic outturns and 7-day ahead forecasting. And Alistair's presentation is entitled Integrating Solar PV into Electricity Networks. Alistair, the floor is yours.
Cool. Thanks, Philip, and thanks, Nikki, for the introduction. I guess my slides are sharing it.
Yeah, we can see them.
Great, brilliant. So hopefully I can build a little bit on Nikki's excellent introduction and give a bit more insight into, these issues around integration of solar PV. My group here at the University of Sheffield have been developing and providing kind of outturn monitoring for National Grid ESA over the last 7 years now, since 2016. So we provide a half-hourly and 5-minute the measurement of the total photovoltaic power generation in Great Britain, and we do that so that National Grid can forecast solar as part of the overall demand forecast for electricity across the network. So I'm going to try and explain a little bit about how that kind of service works, but in much more widely in terms of the context of solar in the network. So here we go. I'll start with a bit of a summary that I say hopefully adds a little bit to what Nikki was talking about in terms of the kind of global and national context of solar as part of electricity systems, and then talk about the impacts of solar on the network and how we kind of can manage them. So I think it is worth starting by pointing out globally that the International Energy Agency expect that by 2027, 2028, solar PV will be the largest installed capacity of any electricity generation technology globally. So this really takes solar from a kind of marginal technology in 2010 to a dominant technology by the mid-2030s. I would say this isn't energy generation. This is capacity to generate energy, and there's quite a big difference in that when you're talking about solar, because obviously only a small percentage of the time the solar is generating at full capacity. So we have this thing called capacity factor, which for solar is in the UK is around about 12%. In other locations around the world, it can be up to kind of 20–25%. But solar is a big deal, as is wind. The next point to make is that transition is coming with a kind of commensurate reduction in the carbon intensity of electricity. So this is a little graph of the carbon intensity of Great Britain's electricity from the kind of instigation of the electricity network back in the 1920s, all the way up to the kind of almost the present day. And it kind of shows this transition from a system that was initially dominated by coal generation, and we switched on a few nuclear power plant in the 1970s, and then a whole bunch of gas came online in the 1990s. And the recent transition from 2010 is the introduction of significant renewable generation from wind and solar. And you can kind of start to see that yellow block at the end changing the carbon intensity of the network substantially, and that will continue. So we're kind of, I like to think we're on the right track here in terms of decarbonisation of the electricity mix. And with that comes a change in the way the system runs. So historically, we kind of had one-way power flows, and Nikki's kind of introduced this already. We had a few power stations providing electricity in a one-directional power flow to the end consumer. And the control of this system was relatively simple. Power stations were kind of, I guess, turned on and off as and when the market for that power required it. And as we go into the future, and actually kind of currently, in fact, we've got a lot of two-way power flows through the infrastructure that was meant for one-way power flow. We've got obviously millions of consumers of electricity, but also millions of generators now. The total number of solar PV systems in Great Britain is over 1 million, probably something like 1.1 million. We have a lot of battery storage already online and a significant amount more in the pipeline. And we have huge numbers of control mechanisms now to make sure that the system is managed. I'll talk a little bit about that. And some of that control is more automatic. And the final issue is that the amount of electricity that we're talking about will increase significantly in the future based on the electrification of transportation and eventually heat as well. So we're talking about adapting a system that was designed for one purpose to something which is actually significantly bigger, better and more automatically controlled. Okay. So PV systems, I think it's fair to say, are kind of unique in terms of a generating technology because they're completely modular. And this is kind of remarkable, actually, that the same technology can power a residential property at a couple of kilowatts, all the way up to kind of utility scale systems of hundreds of megawatts. So that's kind of 6 decades change in size of the system, but the way that the power from those systems connects into the electricity system is actually then slightly different. So we need to understand a bit about the way these power systems at national level are configured, and Nikki's also already introduced some of this, and then we can talk about the impacts of the solar power within the network. So I think it's worth kind of defining what an electricity system is. I think, well, this is my definition, whether it's strictly speaking correct or not. I talk about a network of generators and consumers that all operate at the same AC frequency, where the supply and consumption of electricity are balanced at all times. So that the kind of geography that defines the system is obviously important. So we talk about the Great Britain electricity system, and that's to basically say that Northern Ireland isn't part of the Great Britain electricity system, even though it's part of the same country. Actually, Northern Ireland is part of a system which includes Southern Ireland, so it's an island of Ireland electricity system. And similarly, other countries around the world have their systems divided up by the geography of the country in which they're operating. So in America, there's a variety of numbers of different systems, some of which are connected together and others which are completely independent. And it's the same in Europe. So these AC grid systems, as asynchronous, they're operating at the same frequency, but they can be connected together asynchronously through kind of DC interconnection cables. So Great Britain has a number of DC interconnections to Ireland and to Europe and to Scandinavia. And so then electricity can be passed between the different systems in order to balance supply and demand as well. All right, here we go. So Nikki's already shown something very similar to this, showing that the Great Britain grid, controlled by National Grid ESO, with a set of transmission wires that are owned by National Grid Transmission, and then a number of distribution companies that then take the transmission electricity and move it around to the consumers. These distribution networks are relatively hierarchical in that they go up in terms of the voltage at which they operate, so that they can transfer this power down from the transmission network. Okay, and I've included a little map of the network in terms of the kind of circuit diagram. So each of the shapes on that map is a large power generator, and each of the kind of thin black lines is one of the transmission wires. So what happens with solar PV? So all these systems feed into the electricity network at different voltages. And in a sense, the PV power flow is the wrong way in a traditional sense. And it kind of reduces the power flowing the right way. So we see a net reduction in electricity demand within the network. And we see that net reduction within individual buildings, homes. We see it within the low voltage network, and we see it higher up in the transmission network. And I suppose there are 3 possible issues. There's an issue in terms of reverse power flows, and we'll consider this briefly. There's an issue in terms of balancing supply and demand, since this PV power flow reduces the apparent demand nationally and regionally, and that makes it harder to forecast the demand that needs to be generated by other sources. And that's been an issue since around 2015, and it continues to be an issue. And then the issue that Nikki was talking about was network congestion. And this is a very big issue at the high voltages, and it's going to become a massive issue at low voltages too. So reverse power flows, and I've taken from Road Knight Taylor here, saying basically there's not an implicit issue in terms of the way transformers work. Transformers can convert from high voltage to low voltage and low voltage to high voltage. But certainly if the power rating of the transformer is exceeded, that's going to be a bad thing. And some components, some of the control components might not work under reverse power flows. So only certain substations will be able to support high reverse power flows, and there might be some replacement work to do there. And the final issue is that if there's a lot of reverse power flow, then consumers might end up with having very high voltages on their local network. And this could cause problems, especially for solar PV, actually, in the sense that the inverters that tie the PV system to the grid have a cutout voltage. And if the local voltage goes above that cutout, then the PV disconnects. So there are issues, but they're not the major ones at the moment. This is an example of reverse power flows in reality at one of the largest substations on the Great Britain network down in Cornwall, the Indian Queen's substation. And we see that as the PV output increases through that substation, and this is modeled data from the PV Live service that we deliver, then the demand measured through the substation reduces below zero. And we have these high reverse power flows through that substation. There are several other grid supply points where there are also reverse power flows. The first issue then that I really talk about explicitly is that of balancing. So supply and demand within the electricity network needs to be completely balanced. We need equal supply and demand. And this is done by turning on and off generators as demand changes. And historically, this was relatively straightforward. Demand was relatively predictable. The system operator would make a plan, and there were markets in play in terms of deploying particular power stations to generate the electricity that was needed. Any difference between the kind of day ahead plan was made up through what's called the balancing market, basically power stations turning on a little bit more or other generators turning on to make up the difference, or switch off. And then finally, there's a kind of reserve generation that balances at the minutes and seconds timescale. And this could be pumped hydro or diesel generators or big spinning flywheels. So this is kind of the historical picture for balancing. And to a certain extent, this is still the case today. But now we have huge amounts of embedded capacity, PV, but also wind on the network. And this means the net demand that we see on the network is lower, and the percentage error in demand is likely to be higher. So the picture on the right here shows, this is July 2023. So we have the blue section here is PV generation. I'm colorblind, so I've got no idea what color these are, but the wind bit at the bottom, and then in the middle we have dispatchable generation from gas and biomass, and also interconnection to other countries, and a tiny little bit of coal generation. There's also a block at the bottom which is nuclear, but I think you can kind of see straight away that nuclear generation really doesn't help a huge amount when it comes to balancing supply and demand. So the dispatchable generators that are on the network have to be turned on and off in terms of coping with the embedded generation from the PV and the wind. And in order to manage this, we've got to be able to plan and forecast demand based on both the actual demand, the true demand, which is the top of the line here, but also the net demand, which is the demand that's actually seen by the electricity system operator, taking into account the PV component, which is over and above that. And this is where our specific work here in Sheffield comes in. In order to forecast the embedded PV generation, we've got to be able to measure it. And in Great Britain now, there are about 1 million systems with a total capacity of 15 gigawatts. So at peak, around about a third of all electricity generation comes from solar NGV at the moment. So what we do is to make a map of where all of the PV systems are and how big they are. We also need to know when they were installed and which direction they face so that we can estimate the yield of the system. And we also need to know where they're connected in terms of the topology of the electricity network. We then measure a real sample of systems in real time, a few thousand systems, measure the output in real time, and then scale up using a number of different algorithms to estimate the national output. And none of the data within the scheme is known perfectly. So understanding where the uncertainty is within the schema is important in terms of providing an error metric against the monitored value. We get between 5 and 10% error in total. And so that's our kind of job as part of the service we provide to National Grid. And that service has been in place since 2016 now. Okay, so the second issue on the network is congestion. And I think the bit that I'll focus on right now is about operational congestion, which is managed by transmission constraints. So basically turning off and curtailing generation when there's too much in a particular place on the network. And I'd use the same graph again here and show an event, looks like 16th of July. There was a huge amount of wind on the network. There was also quite a lot of solar. And at a certain time, it was quite evident that there was too much wind and we were going to end up with a kind of scenario where we had way too much generation. So some of that wind was curtailed, switched off deliberately so that the network could retain balance. This constraint management is expensive. It's currently around about £500 million a year spent on constraints, and that's expected to rise to a peak in 2030 to about 2 billion, because there's just not enough copper in the ground to cope with the generation across and around the network. At the moment, this constraint management isn't applicable to the majority of PV plant because the PV plant isn't operating as part of the balancing mechanism. So National Grid don't have control of the majority of PV plant. There's only a few plant that are part of the balancing mechanism. So there's work to be done in terms of developing markets that can be used to manage PV assets that are co-located with batteries in order to such that constraints can be, I guess, managed more cost effectively. So that's the first congestion point. The second is similar to what Nick was saying in terms of network connections. Anything bigger than around about 4 kilowatt peak or 3.68. I think Nicky said 3.64 kilowatt DC AC needs distribution network permission to be allowed to connect. And so the majority of PV at the moment needs permission, and there's this huge queue out to 2037 or beyond. And in terms of solar PV, the majority of that's in the queue now is co-located with battery storage. 100 gigawatts in the queue of PV with battery, according to National Grid ESO's connections registered. So this is the management of these assets and controlling the deployment of the assets alongside the need for that extra electricity generation is obviously a key job for the sector. Okay, so to kind of summarize and conclude, monitoring and forecasting these embedded generation from solar PV is a key control component of modern electricity systems. And it's the same in Great Britain as it is in Southern Australia. And I was speaking to energy policy people in Yukon Territory in Canada, and they've got exactly the same issue in Yukon, even though it's way far north. And they've still got around about the same amount of penetration of PV into their electricity system. Co-located batteries are going to change the way that PV operates as part of the network, and that ought to be a massive benefit, but the kind of regulation around how co-located battery storage and PV has got to evolve a little bit for that to work. And we need data scientists to understand solar to be part of this. Huge amount to be done in terms of developing the systems that manage and operate these plants. So that's good. I have included a little glossary at the end of this thing, but I'll let you take that later. Thank you.
Great. Thanks very much, Alistair. Thanks for the presentation, following on excellently from Nicky, and I'm sure she'll be glad that you name checked Road Night Taylor on the way through. So Once again, I'd like to invite everyone to add their Q&A questions to the Q&A chat function. But until then, I'd like to add one first to you, Alistair. So you obviously highlighted a lot of the constraints and the challenges that lie ahead for PV, or that are indeed already in place. What kind of issues do you see this having on the maximum amount of PV that the UK is able to install in the future, and are there ways to mitigate this?
So I guess the question is, can we get to 70 gigawatts? You see, if you ask National Grid ESO, they say, well, we've got plenty in the queue, thank you very much, plenty enough. And really for carbon, it doesn't matter whether it's wind or solar or co-located. So I think it's the wrong goal, the 70 gigawatts. We need the right goal in the right location, and there needs to be geographic planning in terms of where the best place at the best time is to put these assets. And I say, historically, the network has been upgraded on request when assets have been planned to be put in, and that very kind of reactive planning approach isn't going to work in the future. It needs to be far more proactive in terms of a strategy for how much is needed, when we're going to need it, and where is it going to go. So I think it's a fairly reasonable number for the long run, the 70 gigawatts, but it needs to be put into context of the energy system for it to be practically. There's no point having a goal without a system that can need it or take it.
Yeah, it seems like the context of that goal is the kind of critical thing there, and actually how you do it in practice as well. Once again, if anyone has some more questions, feel free to put them in the Q&A. I do have another one for you, Alistair. So you said earlier in your presentation you're using kind of like the modeling in order to predict to forecast, predict the future essentially. And you've also said that, right on the screen now, we need more data scientists who understand solar technology in this kind of area. A lot of these, with the greatest of respect to a lot of the way people use AI, they kind of use it as a buzzword, but it seems like what you're doing is actually a very good application of it. How do you see that developing over the next few years, and kind of taking advantage of the developments of AI and then applying it to this area too?
So AI is not a monolith. There are many different tools and techniques, some of which are far more closely akin to standard regression fitting, and others which are more sophisticated, I suppose. So yes, of course, the more sophisticated these tools become, the more useful they become. But what we've found is that domain-specific knowledge about how the electricity system operates, how it's constructed, and the quality of data that is accessible are kind of the paramount things. If the data quality was great, you could throw any old AI tool at it and it would work, but the data quality is not great, and understanding the kind of issues with the data in the first place, and then what to do with it, is kind of the key step, I suppose.
Great. I'm sure the audience will be very glad to hear that understanding solar is the key part in that.
It really is.
Cool. Great. Thanks very much. And I invite anyone who has any further questions for Alistair to either put them in the chat so you can answer them later, or to contact him directly. Sure. Alistair Buckley from the University of Sheffield, thank you very much.
Thanks.
Our next speaker is Pat Wheeler from the University of Nottingham, who I believe is calling in from China. Pat is the director of Power Electronics Machines and Control Learning Group, Research Group, and one of his research interests is on the connection of renewable energy to the electrical utility network. Pat's talk is entitled DC Microgrids for Grid-Connected PV Applications. I can see that you've just started screen sharing, so Pat, the floor is yours.
Right, can you just confirm that you can hear me okay?
Yes, we can hear you.
Excellent. Yeah, my laptop's having some connection problems from time to time, so if the slides don't seem to forward, I apologise for that now, but I'm using a different device for the audio. So I'm Pat Wheeler from the University of Nottingham, and I've been interested in the last two talks, and they keep using the phrase that they need to put more copper back into the ground. maybe there's something in this talk which might give an alternative. We'll see. So I'm the head of the Power Electronics Machines and Control Group at the University of Nottingham. And for this talk to work, I need to tell you just a little bit about our research group, because we work on power electronics, electrical machines and control research. And we're a very large research group. We currently have about £40 million of research portfolio and about 165 researchers within the group. So academics, postdoc research fellows, and PhD students. And we're lucky in that 2.5 years ago, we opened a new building. See the picture of it there. And this has given us 5,500 square meters of laboratory space, including some very large labs where we can work at high powers. And indeed, we've got a 5 MVA connection to the, well, it was Western Power Distribution Network. It's now National Grid Distribution Network. And then we can work within that building at power levels up to about 20 megawatts. Because when you're testing electrical machines, you're only feeding the losses into those systems. Voltages up to 6 kV DC and 11 kV AC. So we've got a big facility. I'll point out now that that picture of the laboratory you can see on the screen was taken before we moved in. Anybody who knows anything about university laboratories will know that it's not that tidy anymore. So that's that's the building. Those are the labs, and we're doing this testing anywhere between 2 to 3 kilowatts up to, as I say, up to 20 megawatts when we need to. This building was half funded by the UK government under the RPIF scheme and half funded by the university. And after we'd finished building it, Research England noted that maybe we weren't as close to net zero in this building as maybe they would like. And so they asked us if we could have a look at how to make this building a little bit more closer to net zero, a little bit more self-sufficient in terms of electricity. So on this slide, you can just see the labs there. The big taker of power is the Wolfson High Power Laboratory. We've got various test beds in there. The one thing about that testing is it's discontinuous. We're not taking all that power all the time. It takes us a long time to set up tests, to build equipment, and to break things down after we've done testing, even when we're doing commercial testing, as well as the research work. And so when you look through time, you'll find high peak loads and then quite a long time without too much happening. So we've spent quite a lot of time in the research group looking at microgrids, typically looking at microgrids on aeroplanes, on ships, or amongst houses. And we've worked on both AC and DC microgrids, particularly with transportation platforms, such as aircraft and ships. We're seeing DC microgrids used far more often than their AC equivalents. So the reason we use AC grids, as I think somebody said earlier, is because transformers were a good way to change voltage when we were transmitting electricity over large distances. And that was true before we had power electronics. Power electronics allows us to transmit with DC, and as we'll see in a couple of moments in my talk, that can have a number of advantages. Even if we've got a microgrid, one of these isolated electrical networks, of course we can connect that microgrid to the main electricity network. There's a thought picture here about how you might go about doing that. These microgrids do have the advantage that they can be standalone, or they, in this example, they can be grid connected, or you could, there's concepts where you connect microgrids together and so on. And that can be quite useful if we start looking at particularly rural locations. We had a project, in fact, funded, I always call it a pandemic project because it was funded by the British Embassy in Santiago in Chile during the pandemic. where we looked at putting in a microgrid into a rural agricultural setting. It was actually a vineyard owned by one of the universities we collaborate with out there. So what we were doing there was looking at a very rural location, a location where traditionally they use diesel generators, and looking at how we might build one of these small microgrids with PV energy storage, battery storage, grid forming converters so that we can connect traditional electrical appliances to the network and so on. And to see if we could promote and accelerate economic recovery after the pandemic, but in a way that was going to grow back better and in a greener way. And so we actually also worked with the local community, explaining what we were doing and the benefits of not using diesel generators, something that the price of fuel has only amplified since then. So we had a look at that type of network, and of course it works. And there's plenty of examples of this. One of the things you have to do with this type of equipment, of course, is to make sure it's robust, easy to repair, because some of the locations where you might put this type of system are a long way away from the kind of resources that we're used to when we repair things. So coming back to my new building and coming back to Research England saying, can you do something about this building and make it closer to net zero? So one of the things you'll notice about the building is a typical big laboratory with a big flat roof. And so the obvious thing to do with that big flat roof is put some PV on it. So Research England were very nice to us, and we applied for some money. And the money was to create, it's a project we call Feed MT, and it's a DC microgrid looking at PV generation and battery and hydrogen energy storage as a way of providing the electrical energy we need in the high power lab. So the goal is the testing of the machines and drives that we do in that laboratory to make those as close to net zero as possible. One of the things I didn't expect, but was quite pleasing, was some of the companies we work with, particularly in electric motorsport, were actually quite pleased at this news because they have to operate in a net zero environment anyway. Things like Formula E teams, for example. And this would save them considerable costs in offsetting and so on. So that was the plan, to provide a DC microgrid connecting solar PV, a 1 megawatt hour lithium rechargeable battery, and a hydrogen electrolyzer and fuel cell with some high pressure hydrogen energy storage. So we've got two forms of energy storage and one form of energy generation. So the black line that you can see on here is our existing AC network, connecting the various parts of our building together. What I've called the hotel load there is actually the offices and air conditioning units and all the usual things you have in any large building. What's different for us is that we have a lot of test rigs at quite high power levels within this lab. And the idea is to connect the battery, the fuel cell, the PV generation and the electrolyzer eventually together using what's shown as a pink line on there, which is a separate DC microgrid. And then there will be one connection between that DC microgrid and the existing AC network. What's not shown on there, in fact, is that some of our testing could generate electricity that we need to then dissipate, and actually we can use our energy storage as a way of doing that so that we don't backfeed the grid and so on. So there's various different ways we end up operating different test rigs to make sure that we never put energy back onto the network, that we're always taking energy from the network, or we're taking nothing from the AC utility. So we've got some PV panels on the roof, and I haven't been up on the roof to take a photo of it, so I'm afraid you've got a photo of the PV panels that are out in Chile in the vineyard there. We've got the hydrogen electrolyzer. We already had the electrolyzer and the storage on site. We had to buy the fuel cell to go alongside that. We've got the roof building, which is now covered in the PV panels, and we've got a 1 megawatt hour battery system, and you can see that being delivered on that truck in that photo. And all of this is to provide that energy we need in that high power lab, as well as meeting the idea of making our building a little bit closer to net zero, and to be more better in terms of stability, sustainability, which was important to some of our industrial partners. We also wanted to act as a catalyst to encourage UK industry to adopt this type of technology. And it was interesting in that some of the first inquiries we had when we publicised this work were actually from distribution companies, where they have electric vans that they charge at night, and big roofs on big warehouses where they could put PV panels on during the day. And they were quite interested, particularly in the use of hydrogen, but also in the use of batteries, to get that mix of being able to generate electricity in the day and to charge the vehicles at night without taking that energy from the local utilities, because they were finding that quite challenging when they were trying to very rapidly increase their electric fleet of vehicles. So all this is playing into those themes we heard earlier around making the world a little bit greener, and allowing us to use electric vehicles and to charge those and so on. And hopefully to do that without having to bury more copper back into the ground. The other thing I thought I'd briefly mention in this talk, just got time, is high voltage DC for energy transportation. This was mentioned earlier in these presentations. And there's some good cost reasons why you might use DC rather than AC to transmit electrical energy, particularly over large distances. There's a sort of a very rough diagram in the bottom right there, showing that when you have a high voltage DC system, the power electronic converters, the bits I do as a professor of power electronic systems, are quite expensive. But as is the cabling, when you put cables or wires, this is looking at overhead over large distances. When you put those cables at the bottom of the sea, when you're putting wind farms out in the middle of the North Sea, for example, then the cost of cabling is far higher. And you can see some thought distances there, about 500 miles of overland cabling, or about 35 to 40 miles of subsea cables. Once you get beyond that, you're better off doing a high voltage DC system rather than a high voltage AC system to get electrical energy from one place to another. And we're beginning to see these, particularly with offshore wind farms, the interconnects between countries that were mentioned before, and countries where there are large distances. Picture in the bottom left was one generated by, I believe, ABB many years ago, when they said one of the things we should be doing in Europe is not all sitting as separate countries, but actually connecting countries together using a high voltage DC network, so that you have wind power in the north, solar in the south, and so on. In terms of technology, this kind of multi-port high voltage DC system is very possible. In terms of the political and financial will to actually make that happen across the whole of Europe, I'm not quite so convinced. That would take a lot of political will And I think politics such as Brexit has probably gone in the wrong direction rather than in the right direction. But I have looked at other places in the world. One country I visit regularly is Chile. And Chile is a very long, thin country, as you can see on that map, with great resources in terms of wind power in the south, solar PV in the north, and a lot of users, mines in the north, in the Atacama region, and Santiago in the middle. And that's a little bit of a thought picture on how you might be able to make the backbone of that country a high voltage DC grid. There are some challenges, such as the Andes Mountains that come right down to the sea in the south. But that was a bit of a thought picture on how you might be able to provide a solution and to actually connect the whole of that country together. At the moment, it's split into a couple of networks because of the geographical challenges associated with the topology of the landscape. So a little bit of a thought picture and a reminder that we can think a little bit outside of the UK when we're looking at these solutions. When we're looking at high voltage DC, in terms of the power electronic converters that I work on, it's a fascinating area. And this is looking at connecting to an AC grid from a high voltage DC network. And one of the things we've very quickly realized with this type of power electronic converter is the purchase price wasn't particularly important. What's important is the efficiency of the power converter and the losses over its lifetime. And this is quite good news for us, because this means we can look at various different exotic topologies, which we wouldn't use in other applications because the cost is too high, but which can give us some great benefits in terms of efficiency. Like all things in engineering, you can find lots of papers on lots of different topologies. And when you compare them, you find that there's no perfect solution. It depends what you're looking for. And so we've looked at various modular multi-level converters, various different costs in terms of component count, various different losses in terms of how efficient they are, and various different features. The last one is quite an important one in DC systems, which is the ability to suppress DC faults on the network without requiring extra circuit breakers and so on. Very high voltage DC circuit breakers being quite a challenge technologically and cost-wise. Why is all this important? Well, I keep using this slide because one of the things I find about electric vehicles in the UK is the biggest complaint people have is waiting to charge their electric cars when they're traveling on long journeys. And it seems that the problem there is making sure we have enough electrical energy at the points in the network, in the points in our road network, where we actually want to charge the cars. And this is giving us a lot of challenges. We've done some work in Chile on this because they have very long empty roads in the north of that country, hundreds and hundreds of kilometers without much in the way of towns or cities. And one of the things we've been looking at there is a similar system to the one in my building in Nottingham, which is having PV generation and battery or hydrogen energy storage, so that when a number of cars want to charge at peak times or during the night, for example, there is electrical energy available. But during the day, when maybe it's a little bit quieter in the afternoon or whatever, there can be some generation from the PV. And particularly in the north of Chile, that's a very, very good solution, which could work well for them. So lots of different ways in which we can think about grids, think about the transmission of electrical energy, and think about how we might want to include that in our network. At the beginning of this talk, it was noted I was in China. I'm actually on my way back from Australia. I couldn't talk at a talk about solar energy without putting one slide in about the World Solar Challenge. For those of you who don't know this race, it's a race from Darwin to Adelaide. It happens every 2 years. It's 3,000 kilometres, and we had 45 teams entered this year from 20 different nations across the world. So over 1,000 students from different universities were around for this. And it's notable that the winning team averaged just under 100 kilometres an hour on that 3,000 kilometre route. So maybe the ideas I've shown in here were around trying to make buildings a little bit more autonomous and less reliant on the grid. The other thing that could help with cars is if a car can be driven for 8 hours a day at 100 kilometres an hour along that road, maybe in a lot of parts of the world, our daily commute could be done with solar cars using solar energy without the need for charging those from the grid. So solar car racing really has, in my mind, contributed a lot to the automotive technology that maybe we'll see in some applications in the future. So just to finish, electrification, to my mind, is part of this move towards net zero and sustainability. Microgrid, smart grid technology, DC microgrids in particular, can be part of that solution. One thing I think we're going to learn from our building is that energy storage systems are essential, whether we use batteries, whether we use hydrogen, or whether we use something else. Thank you very much for listening. I hope you've been able to hear me okay all through that talk. Thank you.
Great. Thanks very much, Pat. I can reassure you that, yes, we were able to hear you throughout. You covered so many different topics. Yeah, a really wide view of all that, and the World Solar Challenge, what an adventure that looks like. So once again, I invite you to add any questions to the Q&A function in Zoom. But until then, let me ask you a question first, Pat. You covered a lot of different scales in the areas and the topics you covered, like especially microgrids from your example you gave in Chile all the way up to the building you presented and beyond. Can you shed some light on some of the challenges that are common across all of those different scales, and then some challenges that might come up at the very large or very small scales?
The challenge you have in all those microgrids is the fact that the loads on nearly every network, apart things like aircraft and cars, may be a little bit more predictable. But whenever you put people involved in putting loads on the network, the loads become unpredictable. And you always therefore need forms of energy storage. And you have to manage those forms of energy storage. And that becomes interesting. One of the lessons learnt from the vineyard was the fact that the people were used to just having cans of diesel. And when the diesel generator ran out of diesel, you put some more in it. It's not quite the same with PV energy. Although we were looking at areas where the sun is going to shine all day. People didn't get the idea that they couldn't charge the battery as quickly as they could pour diesel into a tank. And so that interaction and education of how the energy storage is going to work and how you have to plan just a little bit more is something that I think of as common across a lot of these platforms. Even with electric cars, you have to plan your journey a little bit more carefully if you have an electric car where it's going to take you time to charge up, particularly if your charging points aren't as numerous as your petrol stations as we have at the moment. So it's that relationship between the human and the energy storage, I think, is one of the critical things which comes through all of those different examples.
Great. Thanks very much, Pat. Very well said. I'd invite anyone who has any further questions to add them to the chat function, and Pat can get back to you or contact them directly. But for now, Pat Wheeler from the University of Nottingham, thank you very much.
Okay, thank you.
Our next speaker is Rina Sayani from the University of Sheffield. Rina's research encompasses energy access and rural electrification, especially in decentralized renewable mini-grids. exploring energy system modeling and quantifying uncertainties in energy demand. I must disclose that I have had the pleasure of working with Rena in the past, so I'm very aware of her research. Like I say, it's fascinating. So Rena, I'd invite you to share your screen and begin your presentation. The floor is yours.
Thank you. Thank you so much for Phil for kind introduction. And I think I will touch upon something that Patrick has just said when it comes to like when microgrid is like interacting with society or people, everything is very unpredictable. And I think I'll start on that. Can you see my screen?
Yeah, it's just coming through now. Yes, we can see it.
Sorry. Yeah. So I will talk a little bit more from bottom-up side, like the demand side, rather than all generating side. It's all about mini-grids, but mini-grids are mighty. Hopefully, we will find it by the end. So mini-grids for 500 million, and that's what I like to talk about. So around 759 million people are expected to receive electricity for the first time in the next 7 years by 2030. If we want to put a bit of perspective to this number, it's around 11 more countries of this population size of UK. So there's a huge challenge, and I think solar plays a really big role in this. So there are electrification pathways we can currently take up, like grid expansion. All countries have national grids, and that can be expanded, like centralized networks, but then also this decentralized networks like standalone systems or mini grids can also play a very huge role, especially in countries like African Union. So, for example, some of the studies have found optimal split for mini grids that in Africa plays a really huge role. We can see around a 50-50 split. Like it's like the area which are not very close to the central grid, remote and rural, are better served by decentralized mini grids or standalone networks than centralized one. This was just for the example. I think we can dig into let us imagine if you want to put one mini grid somewhere, but how do we really understand what is electricity excess just beyond say electrified or unelectrified? And that's where this is still very crude distinguishing between electricity excess, but still best we have so far. It's like multi-tier framework for residential electricity use for once. Like once people get electricity access in rural areas or remote areas, how they start up, it's not like directly they will go to using all the appliances. It's like they start with lights, telephone, mobile charging, then they put a fan or little tiny more appliances in the house, and then slowly it grows up to like from tier 1 to tier 5. And this multi-tier framework is actually defined based on hours of access to electricity as well as the amount of units used. So yes, very tiny, like tier 1 and tier 2 can be easily provided by solar home system. Like we give individual systems to the homes, and it can provide, but it cannot be scaled, and also maintenance and operations are really difficult with completely standalone systems. But mini grids can also help, like climbing up the tier, like tier 3, tier 4, tier 3. If we interconnect mini grids, I think it can also provide up till tier 5 level of electricity, as well as also Patrick just talked about grid connected microgrids or mini grids. They're also very good way to improve the reliability factor in this kind of scenario. But sizing this kind of mini grids for remote and rural areas is very challenging. As smaller the smaller network we go into, predictability decreases. So if we oversize the mini grid, it's not like diesel that you put more and then you continue using it. If you oversize, it could be higher investments and it impose higher tariff. If you undersize the mini grid, it would be frequently blackouts and people will lose trust in the service. So it is very crucial to design mini grids that are fit for purpose and optimum. And to reach that optimum level, understanding community needs and going from looking at this whole thing from demand side is really important. Also, capacity expansion to adapt to demand growth. That is also one of the very challenging part. Like we can address if we want to scale up the mini grids. So let us just imagine if we want to put one mini grid in some rural area in global south. We just tried with rural India during 2019. So 3 questions we wanted to understand is like, how does electricity demand actually grows after community receives the electricity access first time? And especially we focused on solar mini grids with battery storage. What will be the implications of this demand growth on the sizing approach? How do we consider this demand growth when we are planning the mini grid? And is expanding the capacity after certain years beneficial, or how much it will be beneficial, or how much it will be potential for savings? So mini grids. So we visited some of the mini grids installed by an organization called Gram Urja. If you like, it's very close to Mumbai. It is very unbelievable that like 50 kilometers close to Mumbai, there are so many remote areas because of topography that they are not getting electricity access from the central grid. There are also displacement settings, like some of the dams were under construction. Community had to relocate to some more forest protected areas, and lots of other villages where they were not even considered in census, and that's why they did not get electricity access. So a couple of grids nearby this Kansa forest, which is around 50 kilometers from Mumbai. I visited 6 of these mini grids with Gram Urja and tried to understand community perspective, how they adapt to technology, how they start understanding electricity use in their households. So one of the picture in the center I present is like one of the household which just started having LED lamp and a small fan. This was a community called Talwada, only 58 households, and the solar system, they had around 14.4 kilowatts, and battery size was around 48 kilowatt hour. So very tiny mini grid, very small community, just 58 households, no other businesses around, just like one shop or something. So how I tried to understand how the demand would pick up in long run. And this was just started pre-pandemic, and I had a plan to monitor it long term, but couldn't do it. But this was I could only do it for year 1. So the community in Talwada received the electricity access in March 2018, and I monitored them until June 2019. So I saw around like there was significant growth in electricity use from year 1 to year 2. And yeah, so like around 33% hike in demand growth. Also, it's very seasonal dependent. If summer, like when I visited, it was peak summer, so in the month of April and May, the use is really high because of use of fans or anything, small cooling appliances for comfort, thermal comfort. So this was very interesting part because it would really impact designing the size of batteries, the cooling part, as well as the use of lights at night. And as the network goes smaller, we need to understand how the peak is derived from small community. So thanks to Phil for developing very efficient methodology to understand the demand growth as well as size mini grid. He has developed a tool which is called Continuous Lifetime Optimization of Variable Electricity Resources, Clover. So based on my understanding of mini grids in Talwada, I tried to simulate next 10 years how the demand could grow from the bottom up method. So what we try to understand is slowly we put appliance ownership growing in each household, a number of lights growing, fan, TV, mobile phone, or refrigerators, etc. And then we also put like daily utilization from the survey. We ask people what time they use which appliance, and based on both this input, we try to create like long-term hourly demand profile from small community. And this sets up the basic for how we generate scenarios. Like, so we assume like, okay, the Gram Urja initially provided all the households with 4 light bulbs and 1 charging point. So this is like the dotted line here is the baseline. Okay, we assume that like a control scenario, the demand never grows and it is stable like this. So based on the time of use, of course, the evening is the peak time where people use most of the electricity because all the lights are on. Another scenario is adaptive. Let's say people start growing more appliances. So average adaptive scenario is like for the 10 years, the daily profile looks like this. And there is a target, like, okay, we assume by 2030, certain amount of demand will be reached. And this is generally arbitrarily taken so far. All the developers assume, or there are some ground assumptions based on community engagement that, okay, we can provide, we can assume that by 2030, the demand will reach on daily basis. It's a target scenario. So based on this, we generated stochastic load profiles. And yes, of course, there will be more appliances in use. So technology diffusion, we also use Bars model to predict how the demand will grow based on bottom-up method. And this is what annual profile looks like on the right side. But the key part is seasonality as well. So we can never say it could be any part, like the demand can take any kind of shape in this graph. So we just assume that, okay, what if the demand improves very slowly? Like the cooling appliances have very major role in this because we see it's slowly growing. If people adopt the cooling appliances faster, it will be medium growth, and even faster, then it will be like fast growth. So this can take any shape, and we will try to assess further that how this will have implications on what size of PV and battery we select. So if we say the demand, we used Clover. Clover is also efficient in system sizing optimization. We put some techno-economic inputs about the cost of the system as well as supply mix that we, in this particular mini grid, we thought we included PV and battery only, but it can be having, it can have mix of different supplies. We also calculate, we also try to calculate amount of emissions that would emit, that would be created by mini grids, as well as financial implications, capex or opex, how much it will be required. At the same time, we also took system efficiency into consideration, as well as generation from the renewable Ninja. So based on the stochastic load profiles that we created from the demand scenarios, if we size the battery just based on the baseline demand, like the demand doesn't grow, we would need a smaller system, of course. But if we assume the target, it will be a very bigger system. Like this is generally the case. Right now, most of the developers actually design the system based on arbitrary target growth that, okay, in 10 years or 20 years time. But if we put adaptive sizing, that will, like, we expand the capacity after 5 years, it will be like step 1, which we will call once like multi-step, like, and then change it, expand the capacity in 5 years. That is step 2. That is, so this circles here is like multi-step. We do capacity expansion, and the square is like we give one-off system for the same demand growth. And we then compared what will be the implications of this on the cost. So here I must mention the very unique and novel part of the tools that is developed by Phil, the Clover, that it considers when we calculate the system cost, it considers levelized cost of used electricity and not the generated. Yes, we do have a system that is in place, but it is not necessary that it will be utilized from day one, because people are just introduced to new way of using electricity. Like it's still new technology for really 759 million people. So it won't be picked up very soon, and the generated energy will not be translated into utilization that quickly. So this gives us actual insights into how do we really plan the capital investment into mini-grid. So if we consider a cost of capacity expansion, levelized cost of used electricity in the adaptive scenario, where we expand the capacity in 5 years, it's on an average it's much lesser than the LCUE for the target mini grid. And we also performed some of the sensitivity analysis, where we tried to change a lot of parameters included, like for the slower demand growth, what is more impactful, sizing in multi-step or sizing in one step, like one-off installation. We also considered logistics costs. Will it be feasible for developers to go to these remote sites in 5 years' time and resize the system? What would be the iteration period? How frequently we should resize the system? 2 years to 5 years to 10 years, as well as reliability. It's one of the biggest factor in sizing the batteries. If you want to improve reliability even by 1% from 99 to 100, it would change batteries like dramatically high in the amount. So considering all these different parameters, system cost, degradation, reliability, logistics, attrition period, we came to our analysis also came to conclusion that yes, capacity expansion has some cost saving potentials as well. Other than that, it also proves to be resource efficient. The system, if we give mini grids in like modular system, like we expand in 5 years. So the demand is also met while it's growing, as well as we also curtail the surplus during the first 5 years of time, where we calibrate this with two different factors: demand that is unmet and demand energy that is generated but not utilized. Key takeaways from this paper were like demand growth is actually a very significant driver in mini grid sizing. Generally, most of the top-down model does not consider the social side of the whole technical planning of mini grid, but we must consider that. Multi-step expansion definitely have cost saving potential up to 12%. And sizing adapted to demand growth can be very resource efficient. Also, we can have more granular demand model to improve storage planning and management. If we zoom out from one mini grid and see the global picture again, if like the World Bank has estimated that around 200,000 mini grids by 2030 can provide electricity to 500 million people, and majority of these people, around 400 million, are in African continent. But currently we are very falling short of our target. Like we have only 19,000 mini grids in operation all over the world right now, in the global south right now, and 26,000 more are in pipeline. Mostly all because of the resource constraints. Like we need $35 billion annual investments to continue growing the mini grids in the global south. but we till a date we only have like 20 billion committed to it. If we provide mini grids like mostly renewable based, it will generate around 0.7 rise in emissions estimated, but I think this doesn't include batteries. This is only PV and other wind resources. Current electrification rate is like we are generating 1 mini grid in 12 to 20 weeks because of a lot of regulation issues and resource issues as well. But if we want to reach our target by 2030, we really need to phase up 1 mini grid in 5 weeks in most key deficient countries. I would really like to thank my PhD supervisor, Professor Darren Robinson at University of Sheffield, as well as we collaborated with the research group with Phil at Imperial College London. So I would also like to thank Dr. Paloma Ortega, Dr. Philip, Dr. Oytun, and Dr. Ajay and Professor Jenny. Thank you all so much for the great insights into very challenging topic. As well as thank you for your attention. Any questions?
Great. Thanks very much, Rina. Excellent presentation, and you're too kind to attribute everything to do with Clover to me. There's a whole team behind it, so yeah, it's their great work. Thank you for highlighting the scale of this challenge as well. You obviously zoomed into a few kind of specific case studies of mini grids, but the scale of this challenge is, like you said, 500 million people. So once again, I invite people to add their questions to the Q&A function. But until then, I have a few questions for you, Rina. The first is, you mentioned that in 2019, you were able to go and visit some of the communities that have been using these kind of technologies. Can you share some of the insights that people kind of came back to you about how they use electricity or their kind of big energy issues that they see?
I think one of the key issues with the mini grid, the communities is also in first of all like engagement with the community. From it doesn't go top down with the rural and remote communities. You really need to understand their basic needs. But I reconnected with the same communities post-pandemic very recently, and I think mini grids were really helpful. They also start to set up clinics. They also start to set up small businesses to grow, and unlike like standalone systems, mini grids also provide many opportunities for small and rural entrepreneurs to carry on further activities. So it's not only just domestic use that I covered, but it also progressively they start to use income generating appliances, and that is holistic development in the rural communities. And I think that is one of the best part of having this decentralized systems. But there's also risk of receiving centralized grid connections. So some of the sites also lost mini grid touch because they got central connection that is more subsidized. So the cost of unit electricity from mini grid was around like 40 Indian rupees per unit. But the grid electricity comes for free because it's totally subsidized for rural communities. So yes, there are challenges. I think 2 of the 6 mini grids I visited got connection from national power, so they disconnected with mini grid, but 4 of them really progressed with productive use and holistic socio-economic development.
Yeah, that's great to hear about the kind of the other uses of energy that's come along from those mini grids. Can you shed some light on the different like magnitudes of how much energy is used for a household versus a business versus a hospital?
Yeah, so some of the productive use appliances I recently visited in the same communities where so there are some dry leaf single-use plates, organic or very good plates that is called Patarwadi. So these communities are very much within the forest area. So they collect the autumn foliage leaves and they make plates out of it. So basically they use the machine for pressing down the plates or crop all the that can be used. This was one of the very innovative entrepreneurship model that I have seen in the community, as well as there were some flour meals for basic use within the community. They were sharing. There were also solar water pumps, and I think that was one of the very impactful investment through connection through Minigrid, because it also helped them getting access to water for the agricultural use, and that's like it's also addressing food security as well for them. So these are some of the very interesting innovative ideas people have come up with on the mini-grid. And I think, yeah, some of the mini-grids as well as reached 100% utilization, and they actually wanted more batteries, more PV. So yeah, I also saw capacity expansion in live, like in some of the communities. So there are both sides of the story.
Yeah, that's great to hear. I mean, it's really highlighting the advantages that a technology like PV and battery storage can have in these kind of contexts to provide energy to people who really need it.
Yeah.
Thank you very much, Rina. So if anyone has any
Thank you.
further questions for Rina, please add them to the chat. She can get back to you or contact her directly. Rina Sayani from the University of Sheffield. Thank you very much.
Thank you. Thank you so much.
Thank you. And last but very much not least, we're joined by Mark Letcher from the University of Exeter. Mark's research explores how local government can develop and implement effective policies in light of conflicting local and national priorities and constraints. His talk is entitled Casting Back to the Future PV Policy. Mark, the floor is yours.
Thank you very much, Phil. Just give me 1 second. I'm just going to adjust what I'm doing here. Perhaps you could give me the thumbs up if you can see the slide there, Phil.
Yeah, we can see it. Thank you.
Great, thanks very much. Well, thanks very much for inviting me, and thanks to everybody who stayed on the call. And maybe Friday afternoon or Friday morning. That's very good of you. One of the concerns about going at the end is that either everyone will have said what you're going to say or will have contradicted what you're going to say. I hope neither of those is true. But if you've got questions or comments, I'd very much welcome those at the end. Just to give you a tiny bit of introduction to me, I've spent the last 31 years or so working as a consultant, mainly in the fields of energy and climate change. Quite a lot of that work has been around the development of evidence-based policy for both local and national government. And I've worked for local authorities as a consultant and also as an employee. And the thing that particularly interests me is how we can get better policy and how we can get better evidence-based policy. And what I thought to talk about this afternoon is a paper that myself and my colleague, Jessica Britton, who's actually my PhD supervisor, and I published early in the year, thinking about using backcasting as a way of trying to get better policy around PV, particularly in urban and semi-urban areas. The background to this piece of work, I think, really goes back to the IPCC special report, which was published in October 2018. And this was the report that came out of the COP in Paris, really asking, what do we need to do to limit global warming or global heating to 1.5 degrees C? And not long after the publication of that report, Bristol City Council, which I happen to live in Bristol, so I'm afraid you're going to hear a fair amount about Bristol. But Bristol City Council, as a council, came out and declared a climate emergency. And I have to say, I was working in the council at the time, and it came as a complete surprise. And what the council pledged to do was to make the city carbon neutral by 2030, which was a colossal challenge. And I'll say a bit more about some of the implications of that in a moment. Since then, I think I checked a couple of days ago, I think about 570 councils have done a similar thing, declaring a climate emergency. Quite a lot of those have set 2030 as a date. Some have gone slightly beyond that to 2035. And there are about 2,350 jurisdictions in 40 countries who are done a similar thing in terms of making their commitment to deal with this. And I think one of the key points to make, without trying to lower the tone by being overly political, is that actually the commitments being made by local government far exceed those by national government, certainly in the UK, and that's even before the most recent kind of rolling back by the Prime Minister. So we already have very ambitious targets nationally, but obviously these local targets go well beyond that. And actually, in a sense, what that shows is that there is a very high level, I think, in some areas of understanding and commitment to actually addressing climate change, which I think has not really been utilised at a national level. And I just leave it at that, but welcome thoughts and comments if you've got that. I suppose one of the reasonable questions to ask is whether all these declarations have actually led onto any actions. Again, I'm going to refer to Bristol, which is the authority I know best. I think in that case, it did. It led to a very significant increase in funding to focus on energy and climate change. I think there was a doubling of the team, which had already been a reasonable number, probably one of the largest teams in the UK, particularly as a number of authorities had effectively dramatically cut or indeed eliminated their teams as a result of funding cuts. So it led to an increase in resources. It led to a number of kind of strategic documents and the preparation of some detailed evidence documents on what would need to be done to meet this target by 2030. So I think one of the questions that I'm particularly interested in is, given the intention and the need to act quickly, how do we get better policy and how do we ensure that policy is more effective when it's implemented? And I think one of the things that sits in the back of my mind when I think about this is around diesel. And those of you who are based in the UK will remember that sort of 15 years ago, there was a push towards diesel vehicles, slightly longer than that, push towards diesel vehicles on the grounds that diesel produced less CO2 than petrol. But what wasn't fully taken into account are the kind of local implications in terms of air quality and particulate emissions. So we can have a defective policy which is implemented well, but may have unintended consequences and externalities which we haven't thought about. Equally, we can have a good policy which is implemented badly, implemented ineffectively, and that can also be very ineffective, or we can have combinations of those. The other example I might give is around biomass, where I think there was quite a strong push towards biomass, particularly in urban areas, and I don't think that was particularly well implemented, and I'm not sure it was a particularly effective policy in the first place. Missed out some of the key externalities. So the question is, how can we do better than this, particularly when we're thinking about responses to these very ambitious commitments which have been made by local government? Now, I think one of the ways that authorities, I know they are already thinking about this, is around increasing the level of PV, particularly in urban areas. And there are a number of reasons why they might go down that route. One of those is that a lot of authorities already have policies on PV. Much of that is focused on new developments, so quite a number of authorities will have a requirement for new development to reduce emissions by a certain percentage. In Bristol at the moment it's 20%, in other authorities it's more than that. And quite often the response to that will be to put PV on buildings. Quite a number of authorities are now developing new planning policies which will go much further than that. In the southwest, a number of the authorities are developing policies for net zero energy, which effectively means that over the course of a year, a building should generate as much energy as it consumes. And the strong implication of that is that buildings should maximize the amount of PV they have. And there are also considerations of policies around getting PV on existing buildings. And I've just referenced a study which was done by the Centre for Sustainable Energy. And this was in response to the 2030 declaration by Bristol City Council. And that study suggested that we would need to go from roughly about 1 in 48 buildings in the city having PV on them to about 1 in 2 if we were to meet this 2030 commitment. So one of the questions in my mind, or one of the questions we've been considering, is if you were to go down that route, what are the kind of policy, market and governance implications of doing that? Is that generally a good thing to do, or is that not a good thing to do? If we are going to pursue it, how do we need to do that? And one route for thinking about that, and it was certainly the point where I started at when I was thinking about this particular paper, would be to think about developing a kind of ground up model. So a sort of dynamic GIS based model where effectively you model all of the roofs in the city. You think about all of the PV that might you put on that. You think about the energy demands and the energy supply, and you kind of map that dynamically. And I think that would be a very effective way of doing that. And I know a number of people have done just that. But actually, that's quite involved and quite a long process. And I realized that it was going to take a long time for me to get to that point. And actually, one of the questions I wanted to ask is there another way that we could think about this, which might be slightly simpler, but also allow us to kind of expand and understand the policy implications without necessarily having to go to that dynamic model? Now, one way of doing that is to do forecasting, which is widely used by utilities and government, which is to think about different scenarios and then to map out what that would be. An alternative to that, or something that's complementary to that, is to use backcasting. And backcasting, I tend to think of as a bit like a thought experiment. It's a bit like saying, well, let's think about a point in the future. Let's think about what we want to have done by that point, and then let's work backwards from that and understand the implications of that. And Amory Lovins, I think, was probably the first person who thought about using this as a technique, really in response to the oil shock in the 70s, oil shocks in the 70s, and felt that kind of forecasting, which was really the way it was being considered at that point, wasn't particularly satisfactory in thinking about the end point of where we might get to. And actually, a more satisfactory way of thinking about this would be to try and think about a desirable endpoint and then work back from that. And that's essentially what we've done in this paper, is to think about some different scenarios and then work back from that. So I said I'd mention Bristol a lot, and because I live in Bristol and I had access through the work I was doing with local authorities to some of the people and some of the data, I used Bristol as a case study in this paper. And what I did was took 3 levels of PV and imagine that the city had this additional capacity installed at some point in the future. The first 2, 366 and 738 megawatt peak, came from a study that the city had commissioned, a LiDAR study, looking at the potential solar PV potential resource across the city. And the third one, 1 gigawatt peak, came from a council initiative about 10 years ago now, where there was a discussion within the city, could we make Bristol the first 1 gigawatt solar city? So I wanted to take those 3 scenarios, imagine what would happen if we were at that level, and then kind of work back to try and understand some of the kind of policy implications from that. Now, one of the key points to make here is this is deliberately a very simplified model. So this is the opposite end of the spectrum from the dynamic GIS model that I mentioned a while ago. And this is a much more simplified model, deliberately so, really to try and understand that, as I say, the policy market and governance implications. So the electricity demand data I took from the National Grid data set. I couldn't find any local data, which I think a couple of people have mentioned would be particularly helpful. That's half hourly data. The PV yield came from an EU database, EU PVGIS database, which is a web-based application, and that provides an hourly yield of PV radiation from which you can work out the yield, and that has a 5-kilometer spatial resolution. So bearing that in mind, I considered 3 points within the city and then model those for a range of different orientations, the same range of orientations for each 3, and then combine the results. And there's a number of things that come from this. The first is that even at the low capacity, that can make a significant dent on the annual energy demand if we were able to use all of the energy which was generated. And I'll say a bit more about that as we go along. And then you can see at the high peak that actually you get, a more significant proportion of the annual demand. All of these figures are based on 2016 data. As would be expected, the actual modelled peak is less than theoretical peak because of the orientation and things like inverter losses. And then what I did was plotted out the estimated demand, which is in blue, and I'm pleased to say follows a similar pattern to the presentations that we've seen today. That's a fairly kind of standard wave pattern on that. and then model the estimated output from the PV arrays at different capacity. The red is the lowest and the purple is the highest there. And then by combining those, we can then see what the net demand is. And as you would expect, you get big daily variation as well as kind of hourly variation in this. So just to expand on that a bit more, just to take 2 days in particular. So Saturday, the 4th of June, 2016, the PV system was producing a fairly modest contribution. The following day, it was exceeding demand, helped by the fact that demand is lower on a Sunday than generally on a weekday. So obviously we get this kind of daily variation as well as this hourly variation. I tend to think of this as 2 waves. So we've got the demand wave, which is the one in blue, and then we've got the supply from the PV system. And by combining those, we get different effects. So at points where both demand and the PV output are rising, we get a flattening of the net demand because one wave is effectively cancelling out the other. But if we have a situation where we have a rising demand and a falling output, then one of the things that we've seen from this model, simplified model, is that you get an increase, what we call slew rate, or the rate of change in the net demand. So that graph, that curve becomes steeper, the slope of that becomes steeper. And actually, that's one of the things which I think is probably one of the kind of potentially significant outputs from this. So before adding the PV, the sort of rising slew rate was probably around 50 megawatts greater at its highest rate. As we start to add PV in, that slope becomes steeper. So even with the low system, that rose to about 145 when it was rising and 170 when it was falling. And then it goes up roughly around 10 times if we're looking at a really big PV array, which would be the 1 gigawatt peak system. So I think from this, I've just pulled out some of what I think are the main kind of policy, market and governance implications. If we look at PV as it stands on the system at the moment, I mean, that would be largely, I think, regarded as a kind of negative load. As we start to really increase the capacity of PV, obviously it becomes a dominant source of what would be the kind of local variability and instability in the system. And that implies that we're going to need some form of demand side response, which a number of people have alluded to today. I think one of the questions implement that, if you do that on the basis of half-hourly modelling, is that going to be sufficiently granular and responsive to deal with the variations in PV output? As it happened today, I was cooking my lunch using the microwave. I have solar PV on the house, and because I'm quite nerdy about these things, I just watched for a bit my smart meter readout, and actually the variation, or the sort of net demand from taking into account the PV was varying quite significantly over that time on a sort of 10-second basis. So one of the questions is, can we get to a point where we can actually model, and a lot of this comes down to cloud cover, in sufficient detail and sufficient granularity to be able to use demand side response, or are we going to need something which is closer to real time, for example, triggered by changes in frequency? The other implication, I think, is that without mitigation, if we just go ahead and stick loads of PV in urban and semi-urban areas, we're going to lose the benefits, because effectively this becomes a problem to deal with rather than a benefit. And that implies that actually we need to be thinking about PV capacity and demand side response and storage in concert together. So we think about how we're going to develop those together. And one of the areas that particularly interests me at the moment, and I'm working on a paper on, is what might be the implications of vehicle to grid and making use of the electrification of vehicles, which most of the time will be plugged in, or most of the time not driving, and therefore can we take advantage of that? And I think the final implication, which again a number of people have touched on today, is that we need a much more, or we're going to need a strategic approach, both locally and nationally, but also with the DNOs and DSOs, so that we can all work together, so that we don't end up with these unintended consequences, externalities that we hadn't really thought about and are going to be difficult to deal with. So that's it from me. As other people have said, I'm not quite sure whether I'm on I suspect I'm under time, but I'm very happy to take questions or comments if people have them.
Great. Thanks very much, Mark. And I'm glad to say that you've continued the trend of all of our speakers being exactly on time. So well done, everyone, and thank you. Thanks for a great presentation, Mark. You obviously have a huge amount of experience in this area, coming from lots of different angles. Once again, I invite people to add their questions to the Q&A function on Zoom, but until then, I will ask a few of my own. So Mark, you said right at the start of the presentation, but also kind of continued the theme throughout, the role of local government in implementing these kind of policies, but also sometimes in the context of how to put this diplomatically, like contradictory or like an unaligned national policy. So I was wondering if you could share some light on how far you think that local governments can push these kind of issues on their own, and perhaps some kind of specific leverage points that local governments can be able to use versus what a national government might be able to.
Thanks, Phil. I think it's a really good question. And the short, honest answer is I don't know. And I think it's quite uncertain. And it's an area which is being kind of continually debated and effectively tested. So just to give one example, as I mentioned, a number of authorities are now developing new planning policies effectively in response to national commitments, but also international commitments as expressed in that IPCC paper. Quite a lot of those will go very significantly ahead of national policy as determined by building regulations. But there seems to be a mixed view by planning inspectors as to whether that's allowable or not. So some authorities have been allowed to do that, and effectively they are bringing forward net zero energy / net zero carbon policies. But in other areas, inspectors are saying that they don't have the authority to do that and are effectively pushing them back to national policy. I think that's really unfortunate, is the charitable way of putting that. It's really inefficient. It's wasting a lot of time. It's also wasting a lot of potential good resource. And actually, we need to really coordinate this much more. And the other thing, which I've kind of alluded to in the presentation and the paper, is that if we're not careful, we'll just siphon that good intention down a bad road, a bad route, and then end up creating more problems. So we need to work much more closely together. We are a long way off from where we need to be, I think, is the honest answer. I probably should say, which I should have said at the beginning, but just to get it on the recording, everything I'm saying is my own view and doesn't represent any of the organizations I work for.
Great disclaimer, always valuable.
Yeah, let me get a disclaimer in at some point.
Yeah, on the subject of local governments as well, I think people might kind of see them as essentially independent from one another. Do you have any examples of how local governments have kind of shared knowledge between each other in terms of their good practices?
Yeah, I do. Actually, in the area that I work in, the 4 unitary authorities have worked very closely together. They're all roughly in the same phase in terms of their policy development cycles, so that's been helpful, and they've all been able to work together in terms of commissioning evidence to support those policies. There are other informal networks which extend to different regions and different authorities, but actually I think there's a huge amount of potential to work more closely together. It's kind of it's a bit absurd, for example, at one authority and an enabling authority both having to go and commission evidence, which might be very similar or could be effectively used and then just kind of amended for local areas. So I think there's a lot of potential to work more closely together. It is happening. It's quite informal, but I think it could go a lot further.
Great, thanks very much. And one last question from me, unless anyone wants to come in with some more through the Q&A function. You're obviously doing research in the kind of academic space right now, and I'm sure most of our members who are on the call right now are kind of coming from that academic sphere as well. But based on your experience working in kind of other sectors related to this, can you shed some light on how this kind of research is kind of taken up by the people that need it in the local governments or indeed national governments? Like, how does the research translate from the first-hand work that you're doing, and then how do you get it into the hands of people that really need to read it?
That's a brilliant question. And again, I've been pondering that, and I don't really know the answer to that, because I think actually probably on the back of some of this academic work, there's probably some practical papers that might come out that could be directed at local government. I think there are some potential routes, things like local government association, and there are a couple of other groups in that ilk where information is shared. A lot of information between authorities is shared informally through sort of networks of people knowing each other. People will often move from one authority to another, and that's a kind of communication route. But in terms of disseminating information more broadly, it's quite a mixed picture. Again, I think there are quite a lot of opportunities to do this. Some of it historically has come from national government, so they have deliberately set about disseminating information. To be frank with you, that a lot of that has gone into abeyance since 2010, but it doesn't mean it couldn't be started up again and done effectively. But yeah, I think it's one of the things we need to think about, not least of which because authorities, quite a number of authorities have obviously set themselves very demanding timeframes, and actually nationally we have very demanding timeframe anyway, and therefore we need to get on quickly, but we need to avoid wasting time on policy which is not going to be effective or is the wrong policy. So it's quite a big challenge.
Yeah, quite a big challenge.
Sorry, that's
indeed.
probably a bit gloomy, isn't it?
No, I mean, I think yeah, I don't know if many people would disagree with you though. Yeah, thanks very much. Thanks very much, Mark. If anyone has any further questions from the Q&A function, please do jump in. But as I kind of pause for further questions, just like to take a moment to kind of wrap up everything we've heard. So, well, my last question to Mark was how we kind of share more information about these kind of things. I guess one way is exactly through these kind of forums. So I'd like to thank once again all of the speakers that shared their time and shared their knowledge on this Friday afternoon or morning, wherever you're joining from. We had a lot of different topics on a lot of different scales, all on the subject of solar grid connectivity. If you'd like any more information from any of the speakers, please do contact them directly, or I guess get in touch with the Super Solar Hub. But on behalf of Super Solar, I would like to thank once again Alistair Buckley from the University of Sheffield, Nikki Pillinger from Road Knight Taylor, Pat Wheeler from the University of Nottingham, Rina Sayani from the University of Sheffield, Mark Letcher from the Exeter University, and the whole Super Solar Hub for joining. I will once again share my screen to show you ways to stay in touch. I'm sure you probably know this already by the fact that you've joined this webinar, but please do look out for more information from the Super Solar Hub, including all the different opportunities for online and in-person events, funding opportunities, other kinds of support, collaboration. And if you want to learn more, please do go to supersolar-hub.org to find more information and follow Super Solar on all its social media channels. Okay, I can't see any more questions, but I think I might have lost the Q&A function by sharing my screen. But once again, thank you very much to all of our speakers and for everyone joining today. Thank you very much.